So implies. This is like the big one. So this is this is really if then. If P, then Q. That's really what implies. Like P implies Q. Like P logically leads to Q. If P is true, then Q is true. That's what we're talking about. It's an if then statement. So it's definitely more interesting than and or, right? The notation, which I will use a lot, is this sort of double not headed, double boned arrow. It's this implication sign. So I don't think I was doing this when I wrote the proof of A times 0 equals 0 on Tuesday, but I could have been writing like this before every from each line to the next, because that's what we were doing. We were using logical implication to sort of say each thing, right? So so what does this mean? This means the best way I've seen it stated is that is the following: whenever P is true, Q is also true. And in fact, that example I gave about every time I go to Mars, I'm greeted by little green aliens. I think that's actually fits into this, like, right? So like, if P is, maybe I should just write this way. If P is a statement, I go to Mars, and Q is a statement, I am greeted by little green aliens. Right? So those could be my P and my Q there. Then my claim was that whenever I go to Mars, I'm greeted by little green aliens. And the question of whether that's true or not was sort of a little bit vexed. And I think this is why. It's because like there's ways to determine whether it's false, right? So when is this false? It's false. I think even somebody said this earlier. If I go to Mars, but then I'm not greeted by little aliens, right? By little aliens. So I go to Mars. I go to Mars, which is P, and I am not greeted by little green aliens. I tried to write it out, so now I'm calling them LGAs. And that is not Q, right? So this is false when you have P and not Q. But I think that means we can make a truth table like that's, and this is the only way it's false, right? It's like, that's what I'm saying. It's kind of like almost like a placeholder or something. It's like, you know, if I don't go to Mars, then it's like, what does that mean? In fact, let's try to make the truth table and just think about this. Like think about it in this context, right? So, I think on the context of this example. So again, we have our 4 possibilities: true, true, false, false, true, false, true, false. So if it's true, I go to Mars, and it's true, I'm greeted by little green aliens, then this is true, right? If I go to Mars and I'm not greeted by little green aliens, that's exactly the case when we said it's false. Yeah. So this was true. This was false. Now the two that start where P is false are kind of interesting. Because it's like, if I don't go to Mars, well, I mean, maybe I stay on Earth, but I'm still greeted by little green aliens. Maybe they come to me. Or maybe they don't, maybe I'm not greeted by little green aliens, right? There's like two possibilities there. So, but this is what I'm saying is either way, because it's not falsified, because we haven't falsified the statement by giving an actual like condition of like, I go to Mars and I'm not greeted by little green aliens. This is where I'm talking, there's this slightly strange default towards true. So these are considered true. Right. So that's kind of, it's a little bit strange. It takes some getting used to, I think, that this is the truth table for implies, but it just kind of makes everything work in math. That's kind of one reason why we do this also. And I have read long philosophical articles about like why this is the right thing to do, but it's probably a little more than we need to do for this course, but it's an interesting thing. If you want to come debate it with me, you absolutely should. But yeah, like this is only false. This is only like false in the sense of being falsified, but given a counterexample in one scenario, and that's the scenario up here, right? And so you can actually see too, like I said, P and not Q. So if P is true and not Q is true, would make that true. And I said that's when this is false. So it's kind of the opposite of this. In fact, you could say that, right. So actually, let me just say this. I could do something here where I'm sort of like trying to combine this. This is like saying we can do P and not Q, but we really want the negation of that, because P and not Q is true if both of these are true, right? If both of these are true, then this is true. And that's the only case this is true. But here we actually want it to be false. So in fact, I want to put a negation sign there. And so there's another way to define the implies as not parentheses P and not Q. Hopefully this is obviously a not sign. Let me try to make it more obviously a not sign. Oh, that's not the right color. P and not Q. Okay, because if we actually build the truth table for that, I claim we'll get the same truth table. So I guess I mean as P implies Q. And you can do it. In fact, you should do it. In fact, I should let you get ahead of me and do it a little, do it yourself, and then I'll play catch up. So like, let's actually build the truth table for this. So not Q. Then the next step could be P and not Q. I'm sorry. Yeah, P and not Q. And then the negation of that, not P and not parentheses P and not Q. So build this truth table and see if you get the same thing as the truth table for implies. Give me a minute ahead of me. Wait, did my screen stop sharing? I looked at something else and I lost the share. Sorry, let me share again. Okay. Is it working out? Are you guys getting the same thing? Yes. Right, so not Q just flips this column. We add those together. The only place that's true, I think, is there. And yeah, and you can see it now that if you flip this column, it becomes the same thing. So yeah, again, a little strange, but this is the truth table for P implies Q.